Hello, dear viewers. Welcome to our Science and Space channel. Today, we're going to talk about an exciting discovery that has shaken the scientific world. This research, reaching the farthest corners of our solar system, unveils the secrets of the depths of the universe. In recent years, NASA and other space agencies have launched a series of missions to explore objects in the Kuiper Belt and beyond. Notably, the New Horizons spacecraft garnered significant attention with its journey to Pluto and other Kuiper Belt objects in 2015. New Horizons revealed detailed features of Pluto's surface and atmospheric properties, uncovering previously unknown surface formations and ice volcanoes. This research showed that Pluto's surface is rich in methane and nitrogen ices, with an average surface temperature of 380 degrees Fahrenheit, 229 degrees Celsius. Beyond these discoveries, the Voyager 1 and Voyager 2 spacecraft continue to explore the outermost boundaries of the solar system. In 2012, Voyager 1 became the first human-made object to enter interstellar space by crossing the heliosphere. Currently, Voyager 1 is about 14.1 billion miles, 22.8 billion kilometers, from Earth and travels approximately 323 million miles, 520 million kilometers, per year. Voyager 2, which crossed the heliosphere in 2018, became the second human-made object to achieve this milestone. These spacecraft collect data on cosmic radiation and plasma density in regions where the sun's influence wanes, helping us understand the conditions in the depths of the universe. These explorations provide significant insights not only about the boundaries of our solar system, but also about other star systems in the universe. For example, the Oort cloud, a theoretical spherical region of icy bodies far beyond the solar system, remains a subject of study. Proposed by Dutch astronomer Jan Oort in 1950, the Oort cloud is thought to be located between 2,000 and 100,000 astronomical units, AU, from the Sun. Objects from this region occasionally get pulled toward the Sun, becoming comets visible from Earth. In conclusion, research at the farthest reaches of our solar system offers critical information not only about our planet and neighboring planets, but also about potential life forms and planetary systems elsewhere in the universe. Such discoveries represent a significant step in humanity's quest to understand its place in the cosmos. Stay tuned to our Science and Space channel for these exciting developments and more. Keep watching. Yes, you heard it right. Scientists have discovered carbon dioxide, CO₂, and carbon monoxide, CO, ices at the edges of our solar system. This is the first time these ices have been observed on trans-Neptunian objects, TNOs, the distant bodies beyond Neptune's orbit. Trans-Neptunian objects are found beyond the orbit of Neptune, stretching across a vast region from the Kuiper Belt to the Oort cloud. This area is filled with small icy bodies, including dwarf planets like Pluto, Eris, Haumea, and Makemake. Because these objects are so far from the Sun, they exist at extremely low temperatures, causing various gases to freeze into solid ice. The discovery of these ices was made possible thanks to advanced telescopes such as the European Space Agency's ESA, Herschel Space Observatory, and NASA's Spitzer Space Telescope. These telescopes, operating in infrared wavelengths, can analyze the chemical composition of these distant, cold objects. Observations from the Herschel Observatory confirmed the presence of carbon dioxide and carbon monoxide ices on the surfaces of several large TNOs in the Kuiper Belt. These findings provide significant insights into the formation and evolution processes of TNOs. For instance, the presence of carbon dioxide and carbon monoxide ices indicates that these objects formed through chemical processes occurring at extremely low temperatures, around 418 degrees Fahrenheit or lower. This suggests that the conditions and chemical composition of matter in the outer regions of the solar system are vastly different from those in the inner regions. The discovery of these ices also opens new avenues for studying surface changes on these objects. These ices can sublimate when exposed to solar radiation, potentially causing seasonal changes and even atmospheric variations on TNOs. Monitoring such changes is crucial for understanding the dynamic processes in the outermost regions of the solar system. In conclusion, the discovery of carbon dioxide and carbon monoxide ices on trans-Neptunian objects provides deep insights into the chemical and physical conditions in the outer solar system. These findings not only enhance current astronomical models, but also guide future space missions and astrobiological research. Stay tuned for more exciting developments in the world of science, as there is still much to discover at the boundaries of our solar system. This extraordinary discovery was made by a research team led by planetary scientists Mario Nascimento de Pra and Noemi Pinilla Alonso from the Florida Space Institute, FSI, at the University of Central Florida. The team utilized the infrared spectral capabilities of the James Webb Space Telescope, JWST, to analyze these findings. Launched in 2021, the James Webb Space Telescope is an incredibly advanced observational tool considered the successor to the Hubble Space Telescope. JWST is capable of high-resolution observations in the infrared wavelengths, allowing it to study the chemical components in the most distant and coldest regions of the universe. These capabilities make it an excellent instrument for examining objects like trans-Neptunian objects, TNOs, at the edges of the solar system. Using JWST's powerful infrared spectrometer, the team led by Nascimento de Pra and Pinilla Alonso analyzed the light reflected from the surfaces of TNOs. These analyses enabled the identification of the chemical components present on these objects' surfaces. In particular, the presence of carbon dioxide, CO₂, and carbon monoxide, CO, ices provided significant insights into the chemical and physical properties of these regions. The research contributes greatly to the understanding of chemical processes in the distant regions of the solar system. The presence of CO₂ and CO ices indicates that these objects formed and have been preserved at extremely low temperatures. The data provided by JWST allows for a detailed mapping of the surface compositions of TNOs, enabling us to track the distribution of matter in these regions and observe how it changes over time. WST's role in these discoveries heralds a new era in astronomy. With its 6.5-meter primary mirror and advanced infrared detection instruments, JWST can reveal even the finest details in the depths of the universe. The data it provides will revolutionize our understanding of chemical and physical processes not only in the outer regions of our solar system, but also in other star systems and galaxies. This research, led by the scientists at the Florida Space Institute at the University of Central Florida, marks a significant step toward understanding the composition and dynamics of TNOs at the boundaries of our solar system. The work led by Nascimento de Pra and Pinilla Alonso will guide future space exploration and astrobiological research. Stay tuned for more exciting developments, as there is still much to discover in our quest to unravel the secrets of the universe. Thanks to the incredible technology of JWST, they examined the chemical compositions of 59 trans-Neptunian objects and centaurs. The results are truly striking. This comprehensive study provided a significant understanding of the chemical compositions of trans-Neptunian objects and centaurs in the farthest regions of the solar system. Centaurs are a group of celestial bodies orbiting between Neptune and Jupiter and are located closer to the inner regions compared to trans-Neptunian objects. These objects offer an important window into understanding the dynamic and complex evolution of the solar system. JWST's infrared spectrometer analyzed the light reflected from the surfaces of these objects, determining the chemical components they contain. Particularly, the presence of various components such as water ice, H2O, methane, CH4, ammonia, NH3, carbon monoxide, CO, carbon dioxide, CO₂, and other organic compounds was detected. These findings highlight the chemical diversity and complexity of physical processes in the outer regions of the solar system. In particular, the presence of water ice and organic compounds provides significant clues about how these objects formed and evolved in the early stages of the solar system. These components help us understand the chemical content of protoplanetary disks during the formation of the solar system and how processes in these disks shaped. Additionally, these findings underscore the significant differences in the physical conditions and activities in the outer regions compared to the inner regions. This detailed analysis of the chemical compositions of trans-Neptunian objects and centaurs allows us to develop a more comprehensive understanding of the evolution and formation of the solar system. Furthermore, the presence of water and organic compounds in these objects suggests their potential biological importance, opening up a new avenue for exploring the potential for life in the outer regions of the solar system. These striking results highlight the importance and potential of JWST in space observations. This observational tool is uniquely positioned to examine the chemical and physical properties of celestial bodies in the outer regions of the solar system and even in other star systems. While representing the beginning of a new era in astronomy, JWST's role in these discoveries continues to excite the scientific community. This groundbreaking study, published in the journal Nature Astronomy this week, suggests that carbon dioxide ice is abundant in the cold outer regions of the protoplanetary disk, a large rotating disk of gas and dust, which is a fundamental component in the formation of our solar system. This finding contributes significantly to our understanding of the chemical composition of the protoplanetary disk, a key component in the formation process of the solar system. The abundance of carbon dioxide, CO₂ ice, in these regions provides an important clue to how atmospheric conditions and the chemical makeup of planets evolved in the early stages of our solar system. The presence of carbon dioxide ice in the cold outer regions of protoplanetary disks provides insights into the chemical processes and conditions in these areas. Specifically, molecules like carbon dioxide existing in ice form reflect the influence of low temperatures and high-density environments in these regions. This finding allows us to better understand the role of the protoplanetary disk in the formation of the chemical compositions of planets and other celestial bodies. Furthermore, the abundance of carbon dioxide ice in the outer regions of the protoplanetary disk may also help us understand the chemical compositions of the outer planets, Jupiter, Saturn, Uranus, and Neptune, and their moons. This finding contributes to a more comprehensive understanding of the formation and evolution of the solar system. This study, published in Nature Astronomy, examines the chemical composition of protoplanetary disks, a fundamental component in the formation of the solar system. The abundance of carbon dioxide ice in these regions highlights the complexity and diversity of the formation processes of planets and other celestial bodies. Further exploration of these findings will deepen our knowledge of the formation and evolution of the solar system and help us understand similar processes in other star systems. Yeah, absolutely right. Discovering the prevalence of carbon dioxide ice in trans-Neptunian objects provides significant clues to the early stages of the solar system. But that's just the beginning. This discovery prompts us to ask more questions and conduct further research about the formation and evolution of the solar system. For instance, it's important to understand why carbon dioxide ice is so widespread in these regions and what factors influence its formation and distribution. Additionally, this finding may help us understand the chemical compositions of protoplanetary disks and the conditions in different regions of these disks. Moreover, future observations and space missions could be planned to examine the chemical compositions of trans-Neptunian objects in more detail. For example, spacecraft could land on the surfaces of these objects to collect samples, and laboratory analyses of these samples could provide further insights into the formation processes of these objects and the early stages of the solar system. Furthermore, it's important to study the physical properties and movements of trans-Neptunian objects in more detail. Understanding features such as surface shapes, compositions, and rotation characteristics of these objects could help us paint a more comprehensive picture of the formation and evolution of the solar system. In conclusion, the discovery of carbon dioxide ice in trans-Neptunian objects encourages scientists to conduct further research on the early stages of the solar system and the chemical compositions of protoplanetary disks. This discovery triggers new questions and discoveries that will help us understand how the universe and planets formed and evolved. With future studies, we will shed more light on the mysteries of the solar system and develop a deeper understanding of the universe's past. Absolutely, there is a need for further research to understand the origins of carbon monoxide ice commonly found in trans-Neptunian objects in the study. This presents an exciting opportunity for us to gain more knowledge about the chemical processes in the outer regions of the solar system. The presence of carbon monoxide, CO ice, highlights the complexity and diversity of the chemical composition in the outer regions of the solar system. Finding this compound could help us understand the roles of gas and dust clouds, protoplanetary disks, and objects in the evolution processes in these regions. Carbon monoxide can form in the outer regions of the solar system through several different processes. For example, chemical reactions in protoplanetary disks or radiation interactions on the surfaces of icy objects can trigger the formation of carbon monoxide. Additionally, collisions and interactions in the outer regions of the solar system can also contribute to the production of carbon monoxide. However, more research is needed to understand exactly how these processes occur and what determines the prevalence of carbon monoxide ice in the outer regions. These studies could involve a combination of space observations, laboratory experiments, and theoretical models. Space observations could involve examining different trans-Neptunian objects and other celestial bodies to determine the distribution and quantity of carbon monoxide ice. Laboratory experiments could help us understand the formation and behavior of carbon monoxide ice by simulating its formation and distribution. Theoretical models could be used to simulate the formation process of the solar system and the chemical evolution in the outer regions to explain the observations and experimental results obtained. By gaining more information about the origins of carbon monoxide ice, we can develop a more comprehensive understanding of the chemical processes in the outer regions of the solar system. These research efforts allow us to reach a deeper understanding of the formation of the universe and planets, and perhaps explore similar processes in other star systems. Let's continue to follow this exciting opportunity. Dear viewers, the discoveries in these mysterious and cold corners of the universe are bringing us one step closer to unraveling the secrets of our solar system and beyond. While scientists continue their fascinating research, we'll keep you updated on the latest developments. Trans-Neptunian objects and other distant celestial bodies in the outer regions of our solar system tell us a lot about the formation and evolution of the universe. The chemical composition, physical characteristics, and movements of these objects help us understand what happened in the early stages of our solar system and how it evolved. The latest discoveries reveal that carbon dioxide and carbon monoxide ice are commonly found in these objects. This finding helps us understand what factors were involved in the formation of our solar system and the chemical processes in its outer regions. Additionally, studying the physical properties and movements of these objects allows us to better understand the evolution of protoplanetary disks and the formation of our solar system. As scientists continue these exciting research endeavors, we'll continue to share the latest developments with you. These efforts to unravel the mysteries of the universe represent a significant step forward for humanity in terms of knowledge and discovery. Let's keep our passion for science and exploration alive as we journey together to make more discoveries at the boundaries of the universe. Stay tuned to our Science and Space channel as we continue to share these fascinating discoveries and more with you. Exciting developments await, so keep watching. Subscribing to our channel enables you to easily access the latest information about science and space exploration. It opens a window into the exciting world of science and joins you with us on our journey to uncover the mysteries of the universe. Subscribing ensures you don't miss out on our new videos and allows you to stay updated on the latest scientific discoveries, space observations, and technological advancements. Additionally, you can support us by hitting the like button, helping our content reach a wider audience. Until the next video, let's continue our journey together toward new discoveries, knowledge, and curiosity about space. Goodbye for now.